Hello everyone. Today I'm just talk about how to automated find the bugs in Windows 10. Our topic is about logical privilege escalation bugs. First, let me introduce ourselves. We are all from Tencent. Tencent is the name of a company, for nobody works for only 10 cents. And Tencent is also the largest social media and entertainment company in China. We are all from Tencent Security Wenxu Lab. Now we are just focused on real-world security research. And I am Wenxu. Here is my partner, Shi Qing. I divide today's presentations to 5 steps. The first, I will introduce you the logical bugs in Windows 10's system services. And then we'll do some case studies based on historical bugs. Then we will know how to do bug discovery and automate this processing. Finally, we'll do some works about exploit development. So you may ask me why I choose logical bugs. The first is about stability. So all of us knows that memory corruption bugs is not already stable. With a 10.1 or other computations, the computators just run their exploit again and then again, but failed. That is very usual. And the second one is it is very easy to exploit. For there is many mitigations in Windows 10 today, just like CFG, DEP, ASLR. That is many mitigations to battle with. And finally, it's very fun to catch those bugs and combine them together to gain privilege escalations. So what could logical bugs do? That is, the answer is all that memory corruption bugs could do, that it could do. And including sandbox escape or code executions and privilege escalations. Today we are mainly focused on privilege escalation bugs. So let's see the pictures. The medium integrated users could communicate with the system services, and system service could do file operations and registry modify, or to copy some handlers, or do some deal operations, just like load some libraries, or do some other things. So, for the examples, we choose 2 bugs for the case studies. The historical examples that we choose are very representative. Example 1 is about arbitrary DSL rewrite bug. After we exploit it, we can gain full control of any file we want. The bug 2 is just about arbitrary file read bug. And then contains the following problems. The first one is a path elimination problems. It's very usual in those vulnerabilities. And the second one is time of check and time of use. And let's see the first bug. It's in task scheduler service. And when we call on ALPC interfaces, we could trigger these vulnerabilities and gain control of any file. But before analyze this bug, we need to know some fundamental knowledge about ALPC. And ALPC is called Advanced Local Procedural Calls, which is a part of Windows IPC. So IDL, which called Microsoft Interface Definition Language, is a bridge between client and server in ALPC. So that ALPC becomes a bridge between the client and the server, and we could use IDL to communicate with system service and call its function. So how could we analyze those interfaces? We need a tool named RPC Viewer. It is a very strong and powerful tool that we could analyze those interfaces. And also, you can see the pictures. The registered ALPC interfaces is marked as green. So that means we could just call it directly with IDL code and our interfaces. But this tool is not very useful in some ways because some data structure may be missing, so that you need to do the reverse engineering by yourself with IDA Pro and fix the data structure. When you are able to fix all data structures, this software could fix it. So the problem is clear. We need to find the target DL file which is related to the ALPC interfaces in RPC Viewer and use IDA Pro to do the reverse engineering. You should be aware of the sensitive operations and some function call, which is to say we grant DSL to some file or delete some file. For these vulnerabilities, we could see the interfaces in the target DL files. And we could find it in the target DL file and reverse it to IDL code. And you will find this code is used to grant DSL to a .jar file. The data structures just look like this. It receives two parameters. The first one is the path, and the second one is the SDL strings, which is a security descriptor for the file. And after reverse engineering, we find the string is just convert to the security descriptor for this DSL operations. And it would use update functions to update the target file's DSL. So we could find it use cannulation bugs to limit the path to task folders. So how can we bypass it? Some of you may know we have some ways to reflect those file operations to another place. But today we are talking about the technology behind them. So my partner, Shiqing, could you please share the details behind them?
Yes. Yes. There are three ways to do this. Junction, hard link, and device map. Let's look at junction first. Windows provides a command named make link in CMD to make symbolic links. This picture shows of this command. We can use this argument G to make a directory junction. As the name says, junction is only can be used for two directories. Can't create with file and directory, or file and file. But what happened in the make link command? Let's take a closer look. Okay, this figure shows the reverse code for the implementation of the make link command. We can see that it invokes the NTFS control file function to create the junction. But what is the NTFS control file? As we know, the Windows API device I/O control is used for communication with kernel drivers from user mode space. In fact, device I/O control will check the IOCTL tab. If the IOCTL is FSCTL, it will invoke NTFS control file function. The NTFS control file function is responsible for handling file system related requests. It receives the partners from the user mode and then create the IRP packet and send it to the file system driver. According to this figure, we can see it invoke NTFS control file with FSCTL set reparse point control code. The import buffer is associated with the control code. When the control code is FSCTL set reparse point, the input buffer is a reparse date buffer struct. Okay, and there is a field named reparse tag in the reparse date buffer struct. It can be set to different values, but the most common values are IO reparse tag symbol link and IO reparse tag mount point. Let's take another look at the previous figure. We can see that the IO reparse tag mount point tag was used when creating the junction. The make link command also has a function to create simple links. It relies on Windows API create simple link. The Windows API create simple link is located in kernel-base.dll, and this figure shows the reverse code of it. We can see create a simple link invoke the NTFS control file with IO reparse tag symbol link. Okay, let's take a small summary. There are two commonly used reparse tag. One is IO reparse tag symbol link, and the other is IO reparse tag mount point. When invoke NTFS control file with IO reparse tag symbol link, the file system driver will create the NTFS symbolic link, and it can be used for file or directory. When invoke NTFS control file with IO reparse tag mount point, the file system driver will create the NTFS mount point. It only used for directory. Okay, we now know how to create a reparse point. The next step is that we want to know what happens when we open a reparse point. When we open a file, the Windows kernel first looks for this object in the kernel object directory, but the kernel object manager only knows the NT path, so a conversation is necessary. For example, when we open C test file, the NT DOS path name to NT path name function converts the DOS path to an NT path. In the kernel object manager, OBP lookup object name is responsible for finding and named kernel object in the kernel object directory. The object directory is composed of directory objects, but if the current path is not a directory object, the OBP lookup object name function will call the pass function of this object type. In this figure, C is a kernel symbolic object. Note that kernel symbolic object and NTFS symbolic links are two completely different things. Because C is a kernel symbolic object, OBP lookup object name will call its pass function. The pass method of the Windows kernel symbolic link object is OBP pass symbolic link function. It converts the symbolic object to the real directory object. Now, the file path is device hard disk volume 9 test file. Hard disk volume 9 is a kernel device object. OBP lookup object name realized it is not a directory object. So, OBP lookup object name will invoke device objects parse function, ALP pass device, and passing the remaining name as argument. The ALP pass device function creates a kernel file object as the context of this open operation. It then creates an ARP packet and sends it to the associated file system driver. But if we have already created a reparse point, FSD will return status reparse to ALP pass device function. Then the ALP pass device return the status reparse to OBP lookup object name function. The OBP lookup object name function will determine the status value returned by the underlying. If its status reparse, it will be passed again use the return value. This is the implementation principle of reparse point. And Microsoft provides some information that how Windows APIs deal with the reparse point. You can find it at MSDN. Some Windows APIs are not affected by reparse point. For example, delete file is not affected by reparse point because when delete file function open a file, it uses NT open file function with the file open reparse point flag, and it will not return status reparse code. We also can use make link command with D to create a hard link. It invokes the Windows API create hard link W. The Windows API create hard link W will invoke NT API NT set information file function. NT set information function allocate a IRP with IRP mg set information major function code and set file information class value in IRP's IO stack location struct. And then NT set information file send this IRP to the device object which the kernel file object associated with. In usual, the device associated with the file object is the file system device. So, the FSD will receive this IRP request, and it will set the hard link. By the way, the hard link only be used for reflect file. Double question mark in NT path is usually pointing to global double question mark path. For example, double question mark global root is pointing to global double question mark global root. But if we point double question mark to base named object through device map, then when we open double question mark global root, the directory we actually opened is base named object global root. The important thing is that all Windows API end up use double question mark path. Therefore, we can use device map to redirect objects that Windows API's operations. For example, proxies A want to open a file named C test path test file. Before the open operation, we create a device map for proxies A, make question mark double question mark point to base named objects. Then we create a kernel symbolic object named base named object C and link it to device hard disk volume 4. Note that the real disk C is device hard disk volume 9. When the proxies A opened file C test path test file, firstly, C test path test file will convert to double question mark C test path test file in ntdll.dll by rtl.path name to nt path name. Secondly, double question mark redirect to base named object by device map. And the OBP lookup object name function try to pass base name objects C test path test file. Thirdly, OBP lookup object name realize the C is a symbolic object, then redirect to device hard disk volume 4 and test path. Test file is the remaining path. So the full path is device hard disk volume 4 test path test file now. Then OBP lookup object name evoke ALP path device and pass test path test file as an argument with hard disk volume 4 device. Now we have redirected C test path test file to D test path test file successfully. Yes.
Okay. Thanks my partner to sharing us so many skills to bypass the path eliminations. So let's just see the solutions for the example 1. We could see that our target is to grant a DSL to a target file. So hard link could be used to do this. If we create a hard link, all DSL set to this hard link could also reflect to a target file. So it is very simple. We just create a hard link to the target file we want to take full control. And then we trigger this ALPC interfaces. So all things is done. Let's see the second vulnerabilities. It is located in Windows installer service. But the most importantly is it is not an ALPC interfaces. It is a function called MSI advise product functions, which is used to communicate with the installer service. The function is to validate the target file, and it would copy the target file. So there is a certain time between the copy happens and the check. You could think if the copied file is read by the normal user, he could break the rule and end up with the privilege escalation. So let's see how to win these risk condition problems. Let's talk about OPLux. For Microsoft, it says OPLux is used to design to reducing network traffic times and improve the response time. But actually, it could use to win the risk conditions at only one time. OPLux is based on the function device I/O control. And you could lock the file, just define a callback functions to it. When the file options actually happens, you'll get notified and just execute your callback functions. That is to say, we could just rewrite the file to junctions to the target file so that we could read it. And another way is a function named read directory changes W. This function is no lock. So that is to say, when we do file operations, we will not concern about the locks. Just like if I lock the file with OPLux, I could not do any operations before the actually file operations come. So it is just used to detect if there is any changes on the target directories. And when the directories actually happens, we could do the operation. And we see the solutions for the example 2. We just use read directory changes functions to do it. But as you can see, we could not use OPLux, so build force is also needed. It takes many times to just try it, and we get notified and rewrite this junction. You could see the POC. We just set read file functions and trying to catch the content. But this vulnerability is not so useful because the CPU rate will reach about 100%. So after do the case study and find so many ways to bypass those safety checks, we need to think about a problem: how to do bug discovery. Many of us knows the technology details, but few of them could find new bugs. I think there is a certain way that we could do it. So I developed IDAPRO plugins to assist us find the new bugs. The main problems for us is actually find the most vulnerable functions and detect if there is any bugs. So let's see the plugins. ADA actually provides a lot of interfaces to help us write its plugins. We could use get function attributes to get a function start address and end address. And then we could use get memories in compiler constructions. A basic block, you could see that in these pictures, is a straight line code sequences with no branches. So following the rules on the right side, we could find all of the above operations and just find the target functions with these plugins. If a target address is in the task segment, then we go back to the step 1 to retry this. So talk is cheap. Show me the code. So let's see the code is very representative to find those vulnerable functions. We just try to find all code blocks and detect if there is some operations. By this way, actually we found one new bug reported to Microsoft. It is located in program completed assistant service. It is an arbitrary file metadata read bug. Also, the main problem for this bug is incorrect impersonation and the time of check, time of use. Let's see this assembly code. We could see this ALPC interface is located in PCA svc.deal. So the functions named get file information from path use a safety check to make sure that the current user has the accessibilities to get the target file's metadata. It first uses impersonation to get current user's token, and then use create file functions to try to open a file. The developers think if the current user is successful to open the file, so he must have the privileges. Then he just reverted to system privileges. So let's see how to break this rule. We just create a file name which is same with the target file, and we lock it with the OP-locks. Then we call the interfaces in ALPC. After we get notified by the OP-locks, that is to say the system service try to open the target file with the current user's token, and we rewrite a junction to the target folders we want to read. And then we bypass a check, and the system service reward to system privileges and get the metadata back to our users. So that is to say we gain the target data with a normal user privilege. It's very simple to write such an exploit. We just need to set OP-locks and get the callback functions. After this bug was found, we have spent many times on reverse engineering just about all the interfaces in the system services. We have rearranged more than hundreds of interfaces, but get nothing because so many people are trying to catch bugs, and it's not easy to reverse all the interfaces. So we started to think how to automate this process and get new vulnerabilities. We may know now we are very easy to build fuzzers and use it to detect memory corruption bugs automatically. Let's see the right side of this picture. It's a very traditional fuzzers. It just generates examples and run it with a target executable, just to detect if there is a crash. So I start to think, is there something similar with a crash in logical vulnerabilities? The answer is yes. But first, we need to know how to catch those sensitive operations. We start to think about process monitors of the system internal tools. But unfortunately, there is not any command line tool. So we make it and left interfaces for our framework to catch it. sensitive operations, just like file operations, is very similar to a crash in catching memory corruption bugs. And it's very easy to validate those operations, just like we validate a crash in memory corruptions if there is any use after free or out of bounds read. And I found two operations is very easy to validate. The first one is set security file. The second one is set decomposition file. And I'll build the framework based on them. And there is a problem. Can we just use these frameworks to automate analyze the ALPC interfaces? But unfortunately, the answer is no. It costs too much time and hard to do reverse engineering. So I get another way how to trigger system service, or that is to say, to interact with them. I just get the thought from the example 2 that I have talked about. It is not an ALPC interface, just a function related to system service. So I say I just write a spider and collect a function list related to system service. And also the details in MSDN should be collected for further usage. The spider code is very simple. We just collect by keywords related to system services and get a list, full list. We could automatically try all of them and catch the operations. We do find some useful things in it or interesting things in it, but unfortunately none of them is vulnerable. So I started to think about the system applications. Every one of us use system applications in Microsoft, developed by Microsoft in Windows 10 in our daily usage. So I started to think about if they should communicate with system service, for there is so many functions to be developed. So this problem is solved by an accident. Let's see the picture. Every one of us knows it is Windows Cloud Stores. One day I just click the install buttons on these applications, and I find there is so many sensitive operations just come. And I find if I need to trigger all of the modules of those applications, the best way is just do UI interactions instead of just do so many reverse engineering works. So let's draw conclusions. First, I clicked execute file list from the system folders and do some random stuffs. So what is the random stuffs? I made up a list just like the following: start and exit the target applications and simulate the UI, the interactions with the UI buttons or press some keys. The applications may interact with the system service and trigger some functions by accident. So, in one word, there is a vulnerability template in our framework. First, I just hook the sensitive operations and do interactions. Second, I just replace the file with a hard link or some other things and validate the DSL of that file. If I try to write something into it, but I success, that is to say it was successful. So I just generate a bug report, which is similar to a crash report in memory corruptions. Let's see the architecture diagrams. It is very simple, right? You guys may ask me, oh, it is so simple, does it really works? You are just kidding me. But actually, we use this framework to catch 4 bugs in just 2 weeks. But 2 bugs are still under fixing by Microsoft. So today we just talk 2 of them. 2 new bugs found by this framework. And all of them is about DSL rewrite bug. It's very useful because you can get full control of any file and write anything into it. And the problems is just the same, our old friends, impersonation and time of check, time of use. The first one is located in ALPC development service. When we start the system camera, it is a Windows app. It would try to call service to gain owner of the settings file. So the settings file is just located in users folders, which any users have the abilities to write anything into it. And the system service will try to set DSL for it. So we just set a hard link and point it to the target file we want to get full control of. The result is the current user is set to the owner of this target file, so that we could write anything, read it, or modify it. Let's see the video for this vulnerability. First, I check the DSL for the target file. You could say there is no access privilege for him. I tried to write something into it, but failed. Then I just delete the settings file and set a hard link to the target file where I want to gain owner of. Now I just start the system camera and do some random interactions, which is we could click the button, just do some keyboard events. And then we could find this operation is triggered. So let's check if it is successful. We just try to write something into it again. You'll find successful. So let's check if the content is really rewrite. Yeah. You'll find the DSL is actually rewrite before trigger this vulnerability and after. We get full control of the target file. It is assigned with a CV number in Microsoft's April security advisory, and the fix for this problem is very easy. Just impersonate with the current user's token so that it could only set with himself's privilege. And the next one is located in standard collector service. There is no impersonation again. Seems Microsoft always forget to add it. When you try to click the debug buttons on Visual Studio, it will do the following operations. First, it creates a srca tch file. And again, it creates with the same file name, but the extension is different. And try to set DSL and get full control of him. We could see it just do this operation without any impersonation, so it just uses system privilege to do those things. So how could we trigger these vulnerabilities? When create such files, we use read directory changes to detect the values of that things and create a hard link before the second file was created. Then we could get the owner of the target file. So if you are from a red team, you may ask me, all of your bugs is about file operations, write something into it. But what I need is command executions. So how could we turn the file operations into a command executions with system privilege instead of just writing something into it with system privilege? So you may think some service, the DL files, libraries could be rewritten, but actually there is a trusted installer protect for those services. You can certainly use a third-party software like Google Chrome or antivirus services to do those things. But what we want is everything is installed by default. You could say most of the Windows service deal or library is protected by trusted installers. Some of them is not protected, but exclusive because of the service is run by default, and it just load the DL files. So when you try to rewrite it, it says, I mean usage. So we need to find something runs only when used and not protected by the trusted installer. So we get one gadget, the XPS printers. It is called Printer Explorer Service. It would get loaded when print a XPS document. The DL file would be modified by the system users. And it was found in a wide exploit of that vulnerabilities. And the target DL file we want to rewrite is located in such folders. When you try to create a hard link to this file and trigger vulnerabilities, you will finally find when the services start running, your deals will be loaded and you will get a code execution with system privileges. You just need to hijack the deal main functions and all things will be done. And here is some reference in our project. We'd like to thank James Forshall for his works towards the logical bug researchers. Without his help, we could not do this project. And my leader, Yang Yu, gave us many advices about how to find new bugs. And Chen Dading, he is an expert in such area and gain the Pontoon's edge competitions. Do you have any questions?
No questions from the audience? No hands? Then I'd like to ask you to give one big hand to the speakers once more.